Solution to bonus problem 2 of dynamics. As you can see, this is our force diagram where our mass 1 and mass 2 are very clearly indicated with their forces. As you can see, the base angles of our inclined plane are indeed different, and as well the actual forces are different as well to account for that disparity in mass. So mass 2 is greater than mass 1, which is shown here. If we look below, we can see those force diagrams resolved here, those the vectors here, and again very clearly indicating that the forces acting on mass 2 are indeed greater than mass 1. What is important to note as well is those difference in the tension force and the force acting parallel to the inclined plane. We can see that they are indeed different, which is to account for that movement because mass 2 is greater than mass 1, and I'll go into that just in a second. So here it says as mass 2 is greater than mass 1, the force acting parallel to the inclined plane, so again that force here and that force here, will be greater for mass 2 than it is for mass 1. And because of that, the force acting parallel to the inclined plane for mass 2 will be greater than the actual tension force acting on the object. The opposite is also true for mass 1, where the tension force will be greater than the force acting parallel to the inclined plane, and we can see that here. So for mass 2, that force acting parallel to the inclined plane is greater than the tension force, which will give it that, which will make it able to move downwards. So as the tension force is less than the actual force acting downwards, that mass will move down that inclined plane, and as such cause mass 1 to be pulled upwards. That tension force is greater than the force acting parallel to the inclined plane. So from that we can get these two main equations, and these are for the net force acting in the x and y directions. So for mass 1, it'll simply be tension force minus mass 1 times g times sine alpha is equal, because it's a net force, mass times acceleration in the x direction. For the y direction, the force in the y direction, or the net force in the y direction, it'll simply be the normal force minus mass 1 times g times cos alpha, and because that is completely balanced, it'll simply be equal to 0, so there's no net force there. Now for equation 2, it is simply the opposite of equation 1, so we have mass 2 times g times sine beta minus the tension force is simply equal to mass 2 times acceleration in the x direction. However, because that acceleration in the x direction is the same in both equations, we can simply make that equal to mass 1 or mass 2 times acceleration. Now, I've indicated here that tension is unique to those masses 1 and 2. However, it is important to note that is not the case, okay? Tension for mass 1 is equal to the tension force for mass 2, because it's the same tension force acting due to that pulley. Yeah, so it's as one mass is moving downwards, the tension force will be equivalent to that force acting parallel to the plane, yeah, because it's sort of an equal act happening there. So if we add both equations 1 and 2, we are simply left with this expression, and if we try and isolate acceleration in the x direction, or simply acceleration, we are left with the expression g outside of m1 times sine beta minus m1 times sine alpha all over m1 plus m2. Now if we get that expression and we sub that into equation 1, so this equation here and here, we are left with this here, right? And once we again do a bit of fiddling around, we are left with that spring tension as a function of mass and the angles, which is mass 1 times mass 2 times g outside of sine alpha plus sine beta all over m1 plus m2. And again, we have to note that tension 1 is equal to tension 2, so it is simply just tension. Now on to part B of our bonus problem. An important thing to note here is that it says the condition for which the masses are at rest or in uniform motion. Now we must remember what acceleration is equivalent to when motion is uniform. Because the velocity is constant and there's no change, the acceleration, which is the calculation for the rate of change in velocity, is going to be equal to 0. So we can recall that we have this expression for acceleration here, and if we let acceleration equal 0, we're left with this expression now, right? And once we times 0 by our denominator here and we get rid of g, we are left with this here. Now we can only do that because we know that gravity, mass 1 and mass 2 cannot be equal to 0. That is our condition for which this is true. Once we have that here, we can simply plus this side over, and we're left with mass 2 times sine beta is equal to mass 1 times sine alpha. And once we divide that here and there, we are left with the conditions for the mass and the angles for which the masses are at rest or in uniform motion, and that's here.